One thing that I did miss on the cathode is that and this is, this pops up. Okay, so when I say something's registry testable, and a lot of times what I'm saying is I see this over and over again in registry review books. So the people who write the registry review books tend to be the people who write and submit questions for the registry itself, which means that if it's in a registry review book, there's a pretty good chance it's going to be on the registry. Right. So if you look on page 117, what you see, first paragraph on the left-hand side, certain types of X-ray tube called grid-controlled tubes are designed to be turned off on and off very rapidly. And in those type of tubes, just memorize this, because it doesn't really make a whole lot of sense. But what it says is that the focusing cup, and we talk about focusing cup, is that thing that surrounds a filament that compresses the stream of electrons so that they strike the portion of the target that we want it to hit, improve sharpness, record detail. Where we have serial exposures, which means exposure after exposure after exposure, rapid exposures, like whenever we're doing cardiac catheterization, um, we want the circuitry to be such that those exposures are made immediately, right? And can be turned on and off very quickly. And in those type of tubes are what we refer to as grid controlled tubes, and the focusing cup becomes the exposure switch. Does that mean you reach inside the tube and hit the, the focusing cup? And the answer is no, but that's where it's actually controlled from. The exposure is actually controlled from that point. So just file that away. There's a very good chance that you're going to run into that in a year and a half whenever you take the registry. Okay. So let me get the notes out. So what we talked about on Wednesday were the external components. We talked about the support systems. We had the ceiling support system. We had the floor to the ceiling and the floor mounted systems, which are kind of one and the same as just connection at the top and bottom versus just a balanced thing at the bottom. In the floor mounted systems, we said that the ceiling mounted systems traveled on two sets of rails, one set of rails, that's two rails in the ceiling, embedded in the ceiling, and then two other rails that are mounted perpendicular to the first set, and they're the most flexible. And then we have C-arm systems, which offer a lot of flexibility, but not as much flexibility as the ceiling systems. As C-arm systems, we've got a lot of different orientations for those. We've got the U-arm systems that hopefully you'll get to see over at Azalea when we get it started, but you certainly see the C-arm systems in surgery with what we refer to as C-arms, so that's portable fluoroscopy. So then we talk about the protective housing and what all it does. It protects against leakage radiation, it protects against thermal shock, it provides mechanical support to the X-ray tube. It's got within it oil to cool the X-ray tube down, and it also has the oil to prevent against electric shock as well. It has some sort of fan system in it so that it, can cool the oil down and therefore cool the X-ray tube down, right? So we've got all that stuff in protective housing. Protective housing protects you against the X-ray tube and leakage radiation that has to be limited to less than 1 milligray per hour at 1 meter. That's also 1 Rankine per hour at 1 meter, same thing. So then we got to the glass or metal envelope. We talked about the benefits to the metal envelope, and that was that if we could engineer an X-ray tube that would ignore that potential difference between the cathode and that metal envelope, which is a conductor, then tanning wasn't an issue in as much as arcing. So tanning is still going to be an issue, but the arcing is not going to be an issue. So arcing is specific to glass tubes, and that has to do with evaporation of the filament, coating the inside of the X-ray tube, and changing the electric conductivity between cathode and anode. Then we had the internal components. We had the cathode, and the cathode really had multiple portions to it. So we had the focusing cup, and we just talked about the purpose for the focusing cup, so I won't redo that. but we had two filaments inside of the focusing cup. The focusing cup is made primarily of tungsten, and talked about the reasons for that. It has a high melting point, but also it doesn't warp whenever we heat it up. It's got a little bit of thorium added to it, and that is because tungsten inherently is very brittle and it'll break pretty easily, so we don't want that to happen. So we've got a little bit of an alloy there. Melting point is 3,410 degrees Celsius. That's quite high. But we do melt the filament eventually, and that's what our tanning is, eventually leading to arcing. So we did say that the arcing was the most common cause for immediate or instantaneous tube death. So, if you start arcing and your X-ray tube is done right away. So we've talked throughout the semester about X-ray tube current and filament current. So we have X-ray tube current at kVp. We don't have filament current before that, and all of that is controlled by your MA. Again, we don't get tube current until we get to kVp. So we talked then also about the space charge effect, and the space charge effect is essentially you can't put any more. Your space charge, your electron cloud is so dense, you can't add any more, right? The only way that you can add any more is by hitting your exposure switch, and then electrons jump across the X-ray tube. But your MA is probably so high that you can't repopulate that filament. And that's where you're at maximum exposure. And at maximum exposure, we are at what we refer to as saturation current. Okay. So that emission limited is what that's talking about, is that you can't give it anymore. So we had the large filament for high exposures, right? And we had the small filament for fine detail. We're going to talk a little bit more about that in the context of the anode. So we started into the anode a little bit, and we talked about stationary versus rotating. Stationary, you're just not going to see in clinical practice and diagnostic imaging. The only place that we're going to see those is going to be, again, in a dentist's office. I went to the dentist yesterday. I should have shot a picture of their X-ray unit. It's a little gun, it's pretty wild. It's just a little bitty thing. So we're going to use rotating, and that is for heat disbursement. We talked about how it is that we can design the X-ray tube in different ways to help with the heat disbursement. We can rotate the anode. If we're using a system that inherently creates a lot of heat, then we can rotate it faster. We talked about the rotational speed in diagnostic is about 3,000 RPMs. In special procedures and cardiac catheterization is closer to 10,000, and CT is closer to 10,000. Also, the size of the disc also goes into that. So the X-ray tube that I passed around, that was just a diagnostic X-ray tube. The disc size is just that you saw. But in CT, they're going to be bigger. Cardiac catheterization is going to be bigger as well. So larger anode, rotate it faster, better heat disbursement, right? So we talked about a lot of stuff. We talked about the target material. Again, it's going to be tungsten for a little bit of different reasons. Some are the same, but the atomic number is a big one. It's not just enough to have a high atomic number so that we can get those slowing X-rays, the brims and the high characteristic X-rays, but it's also very important to have a high atomic number with a high heat capacity. And lead has a higher atomic number than tungsten. But what does it take to melt lead? A stovetop, right? So totally useless for X-ray application, right? So it has to have a high melting point, but also it has to conduct heat well. That was important so that we could spread it out across the face of the anode. But we also talked about the backing might be made of graphite, and the graphite is in an X-ray tube I passed around. I think it has a graphite backing, and the backing made of graphite is to try to keep the heat from going down the stem. And we talked about if the stem and the bearings get too hot, then you start to wear out your bearings, and then it starts. You can actually hear it whenever you have your bearings starting to go out. It starts to grind, kind of like what I was talking about in cars pulling up to the red light. Okay. So some of the stuff I bring up and mention, there's a practical application to it. Your bearings may go out in your car, and you can diagnose that, but you can also diagnose when your X-ray tube's going bad because it starts making a grinding sound whenever you rotor up. It didn't just go zzz, it goes zzz. Your bearings going out. You're looking at a new tube eventually. All right, so that's about where we left off, right? Somewhere along in there. Yeah, we covered a lot of stuff because that was about 15 minutes worth of review of what we covered. Feel a little better about it today? A little bit. All right. So, one thing on page 120, because tube current, because our MA is what controls our tube and our filament current, is what primarily drives our heat. Then naturally, if we have a couple of different things, naturally, if we have a lot of current going through the X-ray tube or just the filament itself, then it's going to increase the heat and it's going to shorten the life of the X-ray tube, right? So there's two things that are beneficial to the X-ray tube. One is that you don't want to mash the prep button and hold the prep button down for a long time. Anybody ever worked with somebody that just had a tendency to mash the prep button down and then give breathing instructions? Zzz, take in a big deep breath. Zzz, blow it all out. Zzz, take in another big deep breath. And finally make the exposure. Horrible practice to get into. You're just wearing your tube out. So short exposure times, as short exposure time as possible, while still accomplishing the things that you need to accomplish. Sometimes you have to rotor up and you have to be ready because your patients sometimes can't hold their breath for very long. So you might go take in a big deep breath, blow it all the way out, take in another big deep breath, and while they're breathing in, you rotor up, right? And then you make your exposure as soon as they stop. There are times that you need those long exposure times or long prep times. You need them, I guess, is not really the right word, but you got to use them. Anybody taking an X-ray on a baby? Yeah. Yeah. Okay. So how's that go? Weirdly strong. That's first off. You can't hold them still hardly, but they move all over the place, and a lot of times if they're crying, you've got to be ready to make the exposure as soon as they inhale. The thing is, they inhale for a split second and they exhale for like 3 minutes, right? So if you're not on your prep button while they're shouting out, I think it was a sophomore. I just saw TJC. It was our uniform and TJC patch. I think it was sophomore. But anyway, if you're not on the prep button, right, while they're exhaling and screaming, then remembering that it takes a full second for the rotor to get up to speed, and you're prevented from making an exposure until it gets up to speed. If you wait until they inhale to prep, you're going to miss it. They're going to be in the middle of their exhalation again, right? So you have to be on the prep button. So you're rotoring up and they go, and they stop. Mash, right? You got to be quick. You can't wait to rotor up in that instance. So there are times that you have to be on a rotor switch for extended periods of time, but most of the time you don't. Also, things like, if you're taking an x-ray on a patient in ICU, sometimes because you're watching the bellows to see when they're inhaling and exhaling, you kind of have to have a longer rotor time, but most of the time you don't. So all of that to say, avoid long rotor times because it just drives your heat, kills your x-ray tube. And the other thing is not having high mass exposure. So the type of exposures that are better for your X-ray tube are also better for your patients, and that's higher kVp, lower mass techniques. Okay, so when you can, those are the type of techniques you want to utilize: a short exposure time and higher kVp. So we talked about the induction motor and how it is that the anode spins, right? So the induction motor is technically a part of the X-ray tube, even though it's not inside the X-ray tube. Okay, it's inside the housing, but it's not inside the X-ray tube. So if we were to be looking down on the rotor end of the X-ray tube, so you've got the envelope, and then you've got the rotor inside, and then you've got the bearings around it. And then outside, you've got, of course, the oil, right? But you've also got the induction motor. Let's make the induction motor a different color. And I'll show you the actual induction motor. So if I can spot it, and maybe somebody can pass it up. I don't see it. I'll grab it. So I showed you the, now I see it. I showed you the washing machine induction motor. It's basically the same thing, okay? It's just a little bit harder to see the individual components on it. So this is actual induction motor off of that X-ray tube that's on the egg crate on that shelf back there. And what it is a coil of wire, and you can see where some of the wires peel off and they go through this core to the opposite side. So each one of these things acts as an individual magnet, right? Because whenever we run electricity through a wire, we create two things: heat and magnetic field, right? So the purpose for these individual things is to make each one of these placements act as an individual magnet. So I'll pass that around, take a look at it. So on the outside of the X-ray tube, we've got this induction motor, and it's just a coil of wire. Green is done. So, and it's just on the outside. So we have to have some sort of ferromagnetic material inside of the stem of the rotor, right? So let's say we put one piece right there, and then we activate the portion of the induction motor that's right here. These two have a tendency to line up, right? So it's ferromagnetic material. We run a current of wire through that, and it becomes magnetic. So it pulls it, right? So it's trying to pull it in that direction. It's not going to move. But if I move it to this next one over here, then it's going to have a tendency to want to rotate. And I know we've talked about this already, but just to go back through it, it's going to have a tendency to want to rotate, so that now this is here, right? You saw how well balanced the X-ray tube is. So if I were to just start the rotation of that thing and then just turn it all the way off, it's still going to continue to rotate, right? Very, very well balanced. But if I don't do that, and then I move it down here, it's already rotating in that direction. Now this is going to try to line up that way. If I turn this one off and I turn this one on, it's going to continue to rotate. So it goes from 0 to 3,000 RPM in 1 second. All right, so you can test that out whenever you get into clinicals. Don't test it out on a patient. You can just set your machine up and just press. Don't even worry about the prep button. Just press the exposure button. Make it a low exposure, so it's not hard on the X-ray tube. Make it a low exposure, something like 50 kVp at a mass or something like that, and just power right through to the exposure button, and you won't get that beep for about a second. And the whole purpose for that is to give this time to rotate so that you spread the heat out. Okay, so it's not even exposure limited. It's exposure inhibited for 1 second so that it gets up to speed, so you spread the heat out. All right, so that's the induction motor. It's outside of the X-ray tube. Remember, this is the envelope, but it's still considered to be a portion of the X-ray tube itself, okay? So the only part of the X-ray tube that's outside of the envelope is the induction motor. Very good, very good. All right. So again, you'll see that throughout the across courses, and as very much a registry testable question. All right, so the other thing is that even if we're not making exposure, even if we don't have our current going through the cathode across the tube, even if we're not on a prep button, we're still going to have friction as the rotor continues to rotate, right? We're still going to have friction in those bearings. So it's not good for the rotor to continue to rotate just on its own if it's not in use. So after you make your exposure, what you'll notice, you can hear the rotor, right? You can hear it. But what you'll notice is that after you make your exposure, the electromagnets automatically start firing backwards to do the exact opposite thing. To instead of rotate it, it slows it down to bring it to a complete stop. Bushong says that happens within a minute. Most of the machines I've worked with, that happens within 5 seconds. It's very quick that it slows it down and it stops. Okay, so the things that you need to know about the rotor, and the things that not the rotor, but the stator, which is stationary. The rotor rotates, stator is stationary. Stator is the electromagnet. That's number one. Your induction motor is your stator, is your electromagnet inside the X-ray tube. All mean the same thing. That's number one. Number two is that to create the rotation, they fire in sequence to bring your rotational speed from 0 to 3,000 RPMs within 1 second, right? It's the only part of the X-ray tube that's outside of the envelope, and after the exposure, they fire in reverse sequence to stop the rotor so that it doesn't wear on the bearings. Okay, so just kind of bulletize things that you need to know about that. And it works off electromagnetic induction, obviously. So then we get back into the focal spot, and a couple of things that Amy has probably covered this semester in intro is that the entire disc is not your target area. The target area is just a small area on the on the bevel portion of the anode. Okay, so we're going to call this the target area. What we do on the target, or what we do with the target, is that we essentially, I don't want to say bounce, but kind of, we send the electrons across to the target area, and we create X-rays in a very shallow area on the target. They don't penetrate the target. These are electrons. They're not penetrating things. So just on a shallow area on the face of the target is where we create the X-rays. And the target, because of how we create X-rays, and the X-rays have to come through the port, right? So we got the oil, and then we've got the window here, and that's a part of the protective housing that goes around. We want to limit our isotropic emissions just to the window, right? So let's exaggerate our window. Okay, let's say our window is that big. Okay, so if I create X-rays right here, and I want that X-ray photon to penetrate all the way through this high atomic number structure to get out of the window over here, what's the likelihood of that happening? Not good. Not good, right? How much of the anode does it have to penetrate to get out over here? None, right? So just in this example, what's your exposure at this end of the window? Yeah, pretty much zero, right? What's your exposure at this end? Greater than zero. So what we can say about that is that on the anode end of the X-ray tube, it's not going to be as dramatic. Even if some of these X-ray photons are created here and they skim the surface of it, we're going to lose some of those before they get out of even that portion of the window, right? So what we can say about that is that on the anode end of the X-ray tube, this is the anode end, and this is the cathode end of the X-ray tube. Anode end of the X-ray tube, our intensity is going to be higher or lower than the cathode end of the X-ray tube? It's lower. We got 0 versus not 0, right? So the cathode end of the X-ray tube, the intensity is going to be higher than the anode end of the X-ray tube. So what? We can use that in imaging. So think about the parts of your body that are kind of wedge shaped and how you could use that. So the foot, for example, foot's a big wedge, right? So if I put my toes under the part of the X-ray tube that has the greatest output, then I'm gonna have too many photons on my toes versus the proximal portion of my foot, right? But if I flip it around and put the fat part of my foot here and the skinny part of my foot here, then I take advantage of this, right? So that applies to the thoracic spine. In some patients, it could be the abdomen. Some patients, it could even be the hip, hip pelvis, hip femur, right? So that is what we refer to as the anode heel effect. Very good. So the anode heel effect, it has a couple of things, and this is what we focus on, the intensity difference between cathode and anode end of the X-ray tube. Intensity is greater at the cathode end of the X-ray tube. If it is easier for you to just focus on one end, then do this. Since we call it the anode heel effect, maybe focus on the anode end. Intensity is less at the anode end of the X-ray tube. The other thing, though, is that our sharpness of recorded detail tends to be greater also on the anode end of the X-ray tube. Okay, so there's not just a difference. Did Amy go through this? Yeah, okay. There's not just a difference in the intensity, but there's a difference in the sharpness of recorded detail. And this is harder to draw out than that. Okay, let's say we've got an object. And the object, again, go with a different color. How's red looking? Pretty weak. Let's go back to purple. Oh, there's another red. That's better. Okay. So we've got an object this big. X-rays are going to be created all across the face of the target area, right? I'm only going to draw 4 possible interactions, but they're going to be created across the face of the target. So what we're going to have then is X-rays created here on the upper end, and they're going to get to the edge of the anatomy that we want to see, and they're going to project a density on our image receptor right like that. Okay, so that's your shadow. And we have sharp shadows, we have not so sharp shadows. Sharp shadows are what we refer to as umbra. We tend to not use that word nearly as much as the other one, which is unsharpness, and that is, should I give you that one? Penumbra. Penumbra means unsharpness. That's your fuzziness, okay? So if I create X-rays here, and again, that's going to go all the way across the face of the anode, I'm just, across the target area, I'm just going to draw these 2 for this end. But if it picks up the signal right here, it's also going to give us a density there. So I'm going to have density all the way across here, okay? Because I have X-ray creation all the way across that. So I'm going to have density all the way across that. So then my object then, instead of being that point little, representation there, it looks like it's that big. Penumbra. Okay. Now let's do the same thing on this end of the X-ray tube. So we've got X-rays created here. They pick up the signal and they give us a density on our image receptor there. And I create here, make a density on our image receptor. Which one has the greater penumbra? Cathode into the X-ray tube. Right. So anode into the X-ray tube, you get a decrease in intensity exposure, but you get an increase in sharpness of recorded detail. Okay, so there's actually two parts to anode Hale effect. Those two things. It's sharper down here, but you get less of it. Okay, does that make sense? A couple of other things about the anode and the anode angle is that whenever your questions are asking you about anode angles, they're going to come to you in degrees. Okay, so if you have one that is at your anode angle is 8 degrees, that's probably going to be your special procedures, what they're using in cardiac cath lab and special procedures for sharpness recorded detail, so they can see the aneurysms in the brain and whatnot. Yours are going to be more like 18. Okay, so what that's referring to is the steepness of this. So the smaller the number, the more vertical it becomes, and all of this gets worse. Okay, so smaller number, more vertical. It gets all of it gets worse, but with that angulation, the smaller the angulation, the smaller the number, the steeper the anode, the greater your sharpness of recorded detail overall. So, can I erase this? Everybody good with this? So what I mean by that is this. Let's say we've got two different anodes. One with an angulation like that. What we get is that the very middle of the central ray is going to be what's coming straight down off the anode. Okay? So what we use in that angulation is we can use a pretty steep angulation, and what we'll get is a projected focal spot that's smaller than our actual focal spot. So our actual area of bombardment is, it's this big, right? So I even drew it all the way down here. So let's go out like that, top and bottom of the filament. So this is smaller than that, right? Okay, so remember the discussion of fluorescent and incandescent lights from Wednesday? Which one gives you a sharper shadow? Did the flashlight or did the fluorescent lights? Flashlight did. Right. So the smaller it is, the sharper the image. Right? So if I were to have an anode angle that was at a perfect 45 degrees, that's going to be relatively close. Then my actual focal spot and projected focal spot are going to be exactly the same size. Okay, so which one is your fluorescent light? The big one. Big one. Okay. So we want that steeper angulation within reason. We want that steeper angulation to give us a better, sharper, finer projected focal spot. Okay. So what we have here is actual focal spot. That's there and also over here as opposed to the projected focal spot, right? So that projected focal spot is going to be what the patient would see if they could look up into the X-ray tube and see the focal spot. It's kind of like, you look at this, it's 40 inches long, or it's 48 inches long, I think, because that's 40 there. So it's 48 inches long, right? How long does it look now? 2 words, not 48 inches, right? So it looks a whole lot shorter. So if the patient's eyes were looking up, that's what they would see is that, okay? So what we've got then is actual focal spot, projected focal spot, and the difference between those two is what we refer to as the line focus principle. So line focus principle means that we can use a relatively large actual focal spot to give us a much smaller effective focal spot. Okay, and that increases sharpness of recorded detail. So some of your X-ray, most of your X-ray tubes are going to have one thing, one bevel. Okay, this is bevel on the anode. Most of your X-ray tubes are going to have one bevel. Some of your X-ray tubes, specifically your special procedures where they're going to utilize a very small focal spot, might have what we refer to as a bibevel focal spot, and that's what you're seeing on page 123. You see your filaments in that case are not side by side, but one is going to be like the large focal spot is going to be at the bottom and a smaller focal spot up at the top, so that we can achieve that very small angulation. Okay, you see that image is figure 7.18 on page 123. Okay, it's bibevel X-ray tubes. You're probably not going to work with those unless you're working in special procedures. So if you look on page 123, also at the table, what you'll see is the focal spot sizes. So with our focal spot sizes, what we get is a couple of different things. One is that we've got a length and we've got a width to them, right? So I only draw two dimensions, right? But they do have a length and a width. That's number one. And number two is that they're it's kind of hard to control exactly how tightly the electron stream is going to get after it leaves the focusing cup, right? Because they're all negative charges and they're going to have a tendency to want to spread each other apart, push away from each other. So even though we have a focal spot, an ideal focal spot that we want to limit the stream to, there's a variance. There's an accepted limit to how big it can be. And what you'll notice is that, the length and the width, like your nominal focal spot, maybe 2 by 2, but it's allowed to be as much as 2.6 by 2.6 by 3.7. So, you have, even though your stated focal spot size may be quite small, the allowable focal spot in that case would be a little bit larger, somewhat larger. The percentage of increase is disproportional. The smaller the focal spot, stated focal spot, the more of an allowance you actually have. Okay, so line focus principle, difference between actual and effective focal spot, that's your line focus principle, and how we control that. Make our effective focal spot smallest is to increase the angulation, make it steeper, smaller number, steeper, sharper. Okay. So if you look on page 124, figure 7.20 kind of demonstrates the anode heel effect and the intensity difference between the cathode and the anode end of the X-ray tube. If you notice, the dead square center of the X-ray beam is going to represent 100% of what you want. But if you look on the cathode end of the X-ray tube, it's at roughly 110. At the anode end of the X-ray tube is more like 80, right? So there's a significant difference between cathode and anode end of the X-ray tube. Right? Any questions on all that? If I missed anything. See anything? Oh, yeah. Also, anode Hill effect. Anode Hill. So, anode Hill effect, both the sharpness of reported detail and the intensity differences are more exaggerated at low SIDs. The longer your SID gets, the more the middle of the central array you're using, and those differences are less significant. Does it kind of make sense?
Can you say that one more time?
Yeah, the effects of the anode Hill effect are more significant at short SIDs, so less significant at greater SIDs because you're using more of the center of the X-ray beam. Okay. So then we need to talk about X-ray tube failure, which we've talked about throughout the semester, but we're just going to kind of sum it up and explain all the different ways that we're going to kill our X-ray tube, some of which we've talked about today. It all has to do with the exception of rough handling, it's going to have to do with one thing, and that is heat, right? So we create the heat here. So your light bulbs eventually burn out, right? So will your X-ray tube eventually burn out. That's what we call open filament. And we talked about how you could diagnose whether or not you had an open filament. You know, if you have a reasonable exposure on one filament and it won't give it to you on the other, probably have a burnout filament, right? So you can still use the X-ray tube on that one filament, but you've got to understand that if you're putting all your big exposures on a small filament, it's going to burn out quick too. And also, if you're putting all your exposures for the ones that you won't find detail on a large filament, you're going to lose some sharpness of recorded detail. So there's some drawbacks. They need to replace X-ray tube. Before you get to the point where it burns out, then it's going to coat the inside of the X-ray tube, and we call that tanning, which increases what kind of filtration? Inherent filtration. It increases inherent filtration, eventually leads to arcing, unless we're using a metal envelope. Very good, very good. So big arc of stuff there, right? So also though, if we don't keep the heat off of the bearings, then the bearings wear out, and eventually you're going to get to a stationary anode, and then you're going to be putting all your heat on one spot on the anode, eventually melt the anode. We also talked about earlier in the semester, if you walk out on a cold day, your windshield is frosty, and you just throw a whole bunch of hot water on it, what are you going to do? You're going to break it, right? So we keep a current, a low voltage current, a low amperage current going through the X-ray tube at all times to keep it warm. But if you didn't have that, you came in and you shot a great big patient, you know, you got your 400 or 500 pound patient, you're shooting a KUB on that patient at 80 kVp of 500 mass or whatever, then you're doing the same thing, and you can crack your or you can break your filament, but you could also crack your anode, right? All of that is due to, in one way or another, heat, right? So, sure I didn't miss something on all that. Cracked up, okay. Long prep times, high mass exposure, burns out the filament, increases tanning, leads to arcing. High heat exposures on cold tubes, cracked anode, open filament, heat to the bearings, we got stationary anode. So good. Y'all got all that, right? And I kind of beat that to death this semester, but. All right, so rating charts is the last thing in this chapter. And I want to put your mind at ease. Rating charts are really kind of a thing of the past. Your machine, if you make too many exposures, your machine's going to shut down. Okay, it's just going to say, yeah, you got to give me time to cool down. So where we used to have to calculate exactly how many exposures you could make on a particular machine with a specific set of technical factors, you don't have to do that. And then we had to look at a rating chart and figure out how long it would take for that X-ray tube to cool down so that we could make the exposures again. We don't have to do that anymore. It's not testable on the registry, so you can look at those charts if you want to, but you don't have to memorize them or figure out how they work, okay? But what you do have to know is how to calculate, and why, I don't know. But you do have to know how to calculate heat units, but it's easy. Okay, so for single phase machine, calculation of heat units is just kVp times MA times time. It's just kVp times mass. That's it. But we have a higher output on a three-phase machine because we have those overlapping pulses, right? So we have greater output, so naturally we're going to have greater heat units. Okay, so with the greater heat units, we have to have a multiplier. So it's still easy though. It's not as easy as it should be. You would think single phase, three phase, then it would be times 3, right? But it doesn't work like that. It's kVp times MA times time times 1.4. Okay, so easy calculations, but you don't have to, worry with the charts. I'm sorry?
The equation for the last one?
For the last one, yeah, for three phase and high frequency is kVp times MA times time. So it's exactly like the single phase, but times 1.4. Okay.
And then the rating charts, like what would be like the, I guess, definition of that?
Tube rating charts would just show you the maximum exposures that you can make on a specific machine at a specific with a specific technique. But again, you can fairly well ignore that entire portion with the exception of the calculation of heat units. Any questions on chapter 7? Any questions over the review for the final, if you've had an opportunity to look it over? Can't recommend that enough. Just go ahead and start looking it over. You got a week off, so I'm not saying study all week, but you might want to look it over a little bit here and there. Take it just a few things at a time. I think it's 7 pages, so take a page a day. Just read through it. Circle whatever you don't get, and there's a lot of redundancy in it. So you're going to see kVp in multiple places. You're going to see MA. You're going to see time in multiple places. So and it's not that I'm putting them in multiple places because I want to be tricky. It's because I want you to know from different perspectives what those things are and what they control. Chapters 8 and 9, again, is anybody unclear on the 2 different ways that we create X-rays, brims and characteristic, and what they represent? Okay, well then the rest of chapter 8 is really X-ray production and emission from the X-ray tube. So X-ray production and emission are 2 totally different things because you got filtration and all that. I would also recommend. I'm going to go ahead and I'm going to take the lecture that I made, the recording I made for the sophomores. I'll go ahead and put it in physics, and I think it's chapter like 15 and 8 is its top. But I'm going to go ahead and copy it over into physics. Take a look at it too. Okay. And let's see, our final in here is Friday that we come back, right? So if you take the opportunity to look that over, then on Wednesday, if you have any questions on the review, we can spend the bulk of the time talking about that instead of talking about emission from the X-rays because you'll already be familiar with it. Okay, so that's my proposal to you. Okay. All right, then y'all have a happy Thanksgiving, and I will see you Monday whenever we come back.
All righty.